All right, good evening, everyone. It's just our class. So today going to be the last part for our BJT chapter, okay, high frequencies analysis. So for high frequency analysis, what we need to concern, okay, are the internal capacitance, okay, inside our active device. So the active device is the BJT. Okay, so there is capacitance, okay, between the junctions. So during high frequency analysis, okay, let me draw it. So for our device, we have PNP and NPM. So that's mean we have a PN junction. Okay. So here is the PN junction. And here is there is a depletion region. So here at the depletion region over here, we can notice, maybe we not by using our naked eyes, okay, there will be a effect of the capacitance over here. When we have the P and N type material, okay, when we put it together, it will create a depletion region. So the depletion region will conduct a capacitance, internal capacitance. So this capacitance only can be observed, okay, during high frequency. So what happened here during high frequencies, the capacitance will affect, okay, will affect our input and also output of the circuit. Okay, input and output of the circuit. So let's see what is the effect. Okay, so here we have amplifier or a device. Okay, I just draw using a block diagram. Okay, so we have an input, V in, and also the device have the output, V out. Okay, so the internal capacitance we can denote it with Z impedance, or you can denote it with C, but here I want to use Z. Okay, so here we have our device. Our device, we have the gain, AV gain. AV equals to V out over VI, right? We have learned this. V out will be equals to V out over VI. So here we have V out equals to AV multiplied with V in. So for the circuit, we know that when we have the voltage supply, okay, there must be a current flow. So we denote it as I input. And then this current will flow through our device and also flow through the capacitance. Okay, so here I denote it as IF or feedback. Okay, so here at the output, we can monitor the V out and also we can monitor the current. So if I label it as I out, here I have the minus IF at the output side. Okay, so here what we can implement, or we want to simplify our circuit. Okay, we don't want to mess up. Okay, so here the internal capacitance over here, Z here, we want to denote it with something. So here we can apply Miller theorem. Okay. So Miller theorem said that the capacitance can be replaced with two capacitors at the input and also at the output. So here is the input node and here is the output node. So at this node, okay, at these two nodes, we represent it with two Z, or so I withdraw the, so here is the Z. This is the Miller input, and here is the, okay, so here is the V out and here is your VI. All right, so firstly, see the circuit on the left side. Here we want to determine how much is your VZ, okay? VZ or the voltage across the capacitance over here, the Z notation. So VZ will be equals to V input minus V output. And then we have V out also equals to AV dot VI. Okay. For what we had here, VZ will be equals to VI minus AV dot VI. So here we simplified the equation, 1 minus AV. And then current, okay, we know here the current in, okay, since this is the amplifier, the current, the feedback, okay, this is the connection between the input and output. This one we call it as feedback or connection. Okay, so here the current in, actually here we have another current. Okay, but here when you have the amplifier, okay, the current that goes in here will almost be equals to infinity. So you get II equals to about equals to IF. Okay. Alright, so here we see on the right side here, since you have the current in over here and the current that goes into your circuit, AV equals to V out over V in. Okay, so here the current here is almost zero because this is same like this. I here is almost zero. So you get II here equals to I that goes to your impedance over here. So Z, I denote it with I small f. Okay. So here you have, if you want to determine your impedance over here, ZMI will be equals to voltage divided with current. Okay, so it will be equals to VI over IF. So VI over IF will be equals to IF here. Oh, sorry, here I forgot to write. II equals to IF equals to this one. You get Z, you have VZ over here. So IF equals to VZ divided with Z. Okay, so we replace this into the equation. So we get VI 1 minus AV divided with Z. Okay, so for this one, just replace the equation into II equation. Right, so here we replace again the II here, we replace it with this because we know that the current in is the same with the current that goes to the Z over here and also the ZMI over here. So what we get is VI divided with IF here is VI 1 minus AV. Okay, we simplify the equation. So ZMI equals to Z over 1 minus AV. So from here, if we want to determine the capacitance or the C will be equals to 1 over Z. Okay, so C will be equals to, this is 1 over Z, so we turn it, the upper equation will be downward and the downward will go to the top. Okay, so C and I will be equals to C multiplied with 1 minus AV. Okay, so we can use this equation. It doesn't matter you don't know how to derive, it's okay. But you need to remember CMI will be equals to C multiplied with 1 minus AV. Right? So for the Z mill output here, okay, so for the output, ZMR will be equals to voltage divided with current. So the current is, this one is, so VR equals to, ZMO equals to VR divided with, so IF here is, you see here is, should be it goes up, right? But now it goes down, so it will be minus IF. So minus IF. And then we just replace with the VR equation and also IF here. So what we get is, IF is, so minus VI in bracket 1 minus AV multiplied with Z. So this one minus and minus, so you get positive. VO over VI, you get AV. Okay, AVZ. So this is minus. So you multiply with 1 minus AV. Therefore, you get AV minus 1. Okay. Then you need to determine the C. CMO will be, turn it around. AV minus 1 divide with AV multiply with Z. So we change it to, okay. So I write it over here. CMI equals to C 1 minus AV and CMO equals to C in bracket AV minus 1 divided with AV. Okay, so for high frequency analysis, we can use this. We can use this equation to simplify our circuit letter. Ustaz Salim?
Dah screenshot.
Okay. Okay, so now, from our previous example, okay, we use the same circuit. So in the previous class, we have determined the mid-frequency analysis using hybrid pi model and also low-frequency analysis using hybrid pi model. So now we doing the high-frequency analysis, okay, by using the same circuit. So what happened? Okay, what happened to the circuit is, so we know that from the theory, it says that during high frequencies, the effect is only caused by the internal capacitance in our active device and also the wiring. First is the internal capacitance. Okay, this is caused by the PN junction. And then the wiring in our circuit. Okay, so the wiring in our circuit, we denote it as the C wiring input and also C wiring output. So at the input, okay, so here our input is at the base. Input at the base and output is at the collector. Therefore, at the base, okay, at base terminal, we draw the wiring, the capacitance caused by the wiring at the input. So we draw it as CWI, okay, CWI. And also at the output here at C, at collector terminal, also there is a wiring output, CWO. Okay, so in between our BJT junction, okay, we also need to draw the internal capacitance. Okay, so here we have between collector and base, we have CBC. We just use the name, the junction name, okay, CBC. And then between base and emitter, we have CBE. And between collector and emitter, we have CCE. So there is 3 capacitances over here, and also the wiring capacitance at input and at output. So here you have 5, okay, 5 capacitance. So the value is given. Okay, so the value is given. Ni salin dulu take note the CBC, CVE, CCE, CWI and also CWO. The CBC also known as C micro and CBE also known as C pi. And so you get 2 pi, 12, 3, 1 pi, 1 pi. Okay. Now you need to draw the, for RE is okay because we didn't draw the wiring capacitance at emitter RE and at resistor RE because our circuit, okay, for this circuit, our input and output is at collector and base. So we don't care what happened at the emitter part. I mean, we don't need to represent any wiring effect at the emitter part. Okay. So now we need to use the hybrid pi model to represent our circuit during high frequency analysis. Okay. So here you have the circuit input and output is at base and collector. Base is your input, collector is your output. So I like to draw it as input on the left. Okay, input on the left, output on your right. And then emitter here. Okay, so firstly, what happened to the capacitors? Okay, same like we draw the mid-frequency analysis. Okay, so the capacitor is fully charged and it allow for the current to flow. Okay, so at the base here, it is connected to RS and VS. So this is RS, VS. So here you have, this is RTH. And then at base to emitter, you have R pi, V pi. Here is C to emitter. So here is the V pi. Emitter, the C is grounded, our short circuit. And then at C, you have RC. And then you have RL. So here is your V out. Okay. Then after you draw your circuit, hybrid pi model circuit, then you need to draw the capacitor. Okay, capacitor for the circuit. Right. So here we have CWI at the input. Okay, so CWI. And then you have at the output, you have CWO. Okay. So you have wiring capacitance caused by the wiring at the input and at the output. And then you need to draw the capacitance between the junction of your BJT. So you draw it. Okay, CBC, you have a capacitor over here. And then CBE, you have a capacitor as well. And also from C to E, also there is another capacitor. Okay, so here when you see this CBC, this is C pi, and this is C mu. Okay, so CBC here, we use Miller theorem. Okay, we use the Miller theorem to represent our CBC. So CBC will be, jadi apa CBC? What happened to CBC? Similar input and similar output. So similar input, okay, so at the base node, okay, at the base node you draw another capacitor. So this is similar input, and then at the collector you draw another capacitor to the output. So this is similar output. Okay, so there is no more CBC, right? Because you already represent it with CMI and also CMO. So CMI equals to, the original capacitor is CBC in bracket 1 minus AV, and then CMO is equals to CBC in bracket
AV
AV
minus 1
minus 1 divide
over
with
AV.
AV kan. Okay, so you replace the CBC that is given in the question. Okay, CBC is 2 micro. Okay, so you denote it here, CBC with 2 micro, and then AV is 200 something. Okay, based on your DC analysis. Berapa AV? Nanti kira lah berapa, sebab you can use the AV from the previous class. Okay, because this is the same circuit. Alright, so here what happened is that, okay, so from this serabut here, from the too many capacitors over here, okay, if you see at the input, okay, at the input part here, because your B and C, okay, the circuit at B and C is no longer connected, right? So you can see that actually your capacitor, okay, your capacitors here, CWI, CMI, and also CPI are parallel, right? So here we can denote it as, this is a parallel capacitor, we denote it as CI, and at the output part, we can see that C mu, CMO, CWO, these three are parallel, so we denote it as C output. Yes, we just use AV that we get from the mid-frequency analysis. Okay, so CI equals to CWI plus CMI plus C pi, and then C output will be equals to, because capacitors, parallel capacitors is add or a sum, okay. If resistor in parallel, you need to divide, but here when the capacitors in parallel, you need to add. So C output is equals to C mu plus CMO plus CWO. Okay, so now you get two capacitors. Yes, CBC is changed to CMI and CMO. Okay. Okay. Can I go to next slide? I want to withdraw, okay, from this equivalent circuit. You can withdraw it. Okay, so here what happened is, the circuit just now you have RS and VS to the ground, and then you have base, collector, emitter to the ground. So this one is RTH, and then at the C you have RC and also RL. So just now we have C output and also C input, C output. Okay, so actually our circuit is simplified like this, and then we can determine the frequencies that caused by these two capacitors. Okay, so here, okay, so for this part, if I simplify the circuit, RS, and then you have RTH, R5, and then here is CI. Okay, and then at the output here, we have C out, RC, and also RM. So here at the input part, okay, GMV pi we can replace it with open circuit. VS we can represent it with short. Okay, so this to make the simplified circuit easy to our eyes to see whether the resistors are series or parallel. So here you can see that your resistor here, okay, so all of the resistors are parallel. And this RC and RL also parallel. Right, so this CI we can get a frequency that caused by the capacitance. So we have FCI will be equals to 1 over 2 pi. The resistor is RS parallel with RTH parallel with R pi, and then multiply with CI, right? Then we get the frequency. And then another one is FCR equals to 1 over 2 pi. Resistor is RC parallel with RL multiply with C out. So you get another frequency. Okay? Cuba kira how much you get. Can you determine how much is your CMI, CMO, okay? And then how much is the frequency that caused by all of the capacitance? Cuba kira sekejap. AV, from your previous class, if I calculate this correctly, AV should be around 215. AV, maybe I'm not sure whether I press the calculator correct or not. AV equals to minus 215. Okay, how much is your CMI, CMO? Attendance ada yang anyone left, I forget to slide in. Well, how much is your CI? CI equals to C omega I plus CBE plus CMI. C omega I plus C pi plus CMI. C omega I 1 pico plus C pi is 12 pico plus CMI. CMI maybe for CBC 2 pico. CBC 2 pico. 432 pico. So this one 445 pico, correct. CR CR is CMO. CMO is 2.01 pico plus CCE. How much? CCE 3 pico. C omega 1 pico. So CR will be 2, 3, 4, 5, 6.01 pico. CI 445 pico. CR 6.01 pico. So just now we already determined two high frequencies, right, for FH. Okay. So from this circuit, we get FCI and also FCO. Okay, so these two frequencies. Alright, so here, for all of your result, okay, it doesn't matter how much is your F. So, how much is your FCI and FC out? Okay, you have two values for the during high frequency analysis. Okay, so if you get, okay, if you get FCO 30 megahertz and another one, FCI, FCI, how much your FCI?
7.32 megahertz.
29. Okay, so if you get 30 megahertz and 37 megahertz, okay, so in your graph, in your gain graph, this is AV in bracket. Therefore, your FCO is 30 megahertz, so it comes first, right? So this is 30 megahertz and 37. Okay, so for your gain, your AV, okay, so for your AV is straight, okay, but until a certain frequency, it will change. Okay, so the changes are caused by the capacitance at the output. So the first capacitance that is near to the AV, okay, we can consider it as the starting point or the at the frequency where the gain is starting to decrease. So we can draw our circuit gain something like this. This is your AV, okay, AV modulus. So at 30, around 30 megahertz, you get a decrement. Okay. So here, okay, for the, if the question asks you how much is the dominant, okay, the dominant, the word is dominant. Dominant high frequency, okay, will be the earliest frequency that is near to your AV. So the dominant high frequency in this case, or if you get 30 and 37 megahertz, so your dominant high frequency will be 30 megahertz. Okay? So later try to recalculate the capacitance and also the frequency, right? Okay, so from the circuit, actually you can do the, firstly you do the DC analysis, and then you do the mid frequency analysis, and then the low frequency analysis, and today we learn about high frequency analysis. Okay, this is, okay. All right, so here is another example. Okay, determine the values of high cut-off frequency for the amplifier circuit shown below. So GM is given, and also the capacitance. And then you need to determine the cut-off frequency. So here the word is cut-off. So what is cut-off? Cut-off means that at which frequency, okay, at which frequency it cut off your gain. So here you can say, so the FCI and also the FCO. So this is one. Okay, we try to do the high frequency analysis first. Okay, so firstly we need to, because when we do the high frequency analysis, okay, we need to know how much is the AV, the gain. Okay, because when we do the Miller theorem, we need to know the AV. So if we want to know the AV, we need to draw the equivalent circuit, right? So here is your, okay, CBE. Base is the input, collector, and also emitter. Here you have bypass capacitor. So emitter to the ground base you have R1, R2 and also R pi. Here is R1 parallel with R2 and then you have RS, BS. Okay, CE you have independent GMB pi. Okay, so C here you have RC and also RL. RC, RL, be out. Okay. So from this, you know that your AV equals to V out over V in. So V out is RC and RL parallel, right? So here you have negative GM V pi RC parallel with RL divide with VI. VI here is equals to VI equals to VR1 parallel R2 equals to V pi. Okay, so here you have V pi. Now you can know that your AV equals to negative GM multiplied with RC parallel with RL. Okay, so now you get the AV value. How much is the AV value? After that, you need to find the Miller theorem for, here you have CBC, right? Okay, so now CBC you represent it with Miller theorem. So you have C Miller input and also C Miller output. So C Miller input equals to CBC in bracket 1 minus AV CMO in bracket, CBC in bracket AV minus 1 divided with AV. So CBC is 3 pico. 1 minus AV is, so AV is minus 60. So minus 60. So given CWO, wiring output, so you draw the CWO, and then you have CWI, wiring input, CCE, CWO, CCE, CWI, C pi. Okay. So CI equals to CWI plus C pi plus C Miller input, and then C output equals to CW out plus CCE plus C Miller output. And then you can find the FCI and also FC out. Okay. So the cut-off frequency, cut-off frequency is the frequency that is near to the AV. So here the less frequency is considered as the cut-off frequency. Therefore, your cut-off frequency is 887 kilohertz. Okay. Okay, let me upload the slide first for you while you calculate the result. Okay, have you found the frequency? Okay, dah siap ke?
Ada.
Okay. So there is another exercise. Okay, so here I just want to give example. Okay, if you have a voltage divider bias for BJT circuit, but the supply are 2, which means you have usually you only have VCC, but now the circuit provide with VEE. Okay, this one is okay. I will give you the PDF after this, but I just want to share how you can do the KVL for this circuit. Okay, so same concept. You apply the Thevenin theorem, right? After that, you simplify the circuit. So now, if I redraw the circuit, here you have VTH, VTH, here you have RC and also VCC. Okay, if you have two supply over here, what you need to do for VTH, okay, if you still remember your circuit theory equation, you need to add on, okay, both the voltage divider concept for both part, which means for R2, you need to multiply with VEE. Right? In our previous example, R2 VEE is 0, so R2 multiply with 0, you get 0. That's why you don't bother much about the R2 resistor. But now you have two source, you have VCC and VEE. What happened to your VTH is, firstly, you have R2 multiply with VCC divide with 1 plus R2, and then you need to multiply with the VEE part. Okay, so VEE part you need to multiply with R1. R1 multiply with VEE divide with R1 plus R2. Okay, so here VEE, okay, if you want to put the value in the calculator, you just put the VEE equals to minus 20. So here, VCC here is positive 20, VEE here is minus 20. Okay, so here what you get is R1 is 8K, R2 is 2K, okay, 8K. Okay, 2K you multiply with 20, you get about 40K, right? But here, 8K you multiply with minus 20, you get 100 minus something, right? So here, your VTH would be minus value. Okay, minus something. And then you put the VTH over here. Because usually our VTH is positive, so we denote it as like this, right? In our circuit. But now our VTH is minus, so easier for us if we put VTH with symbol either with in a circle, or if you want to draw, you need to draw the direction for the VTH is negative direction, like this. Okay, so the easiest is just put it as a in circle, so that when you write your KVL over here, KVL1, you have VTH, same like our previous exercise. What we write is VTH equals IB RTH VBE plus IERE plus VEE. Okay, we don't bother about the minus sign, we just put the label, which is VEE and VTH. We don't write it as minus VTH. If you want to write it as minus VTH, it's also can, but please be extra careful, right? So here, if I want to find the IB, will be equals to this IE equals to IB beta plus 1. So your IB will be equals to VTH minus VBE minus VEE divided with RTH plus beta plus 1 E. So here, if you want to put the value, okay, here your VTH, okay, VTH here will be, this I get around minus 11. So here I write it as minus 11 minus VBE is 0.7 minus VEE. So VEE is minus 20. Okay, so just write it over here. So IB would be equals to, okay, so this one you can do it after this. Alright, so I just want to share, okay, the KVL for the simplified circuit would be the same. However, the value that you need to replace for your VTH and VEE, okay, is according to the amount that are provided to you. So here your VTH, you get minus 11. So you put in your equation, VTH would be equals to minus 11. Okay. And then another KVL over here, KVL2. Okay, I write KVL2 over here. KVL2 will be equals to VCC equals to ICRC plus VCE plus IERE plus VEE. So your VCE, okay, because the question asks you how much is VCE. VCE equals to VCC minus ICIC minus. Okay, so now your VCC, okay, VCC is 20 minus your ICRC, you just put how much is the value, and then minus VEE. So minus VEE is minus 20. Okay, so then you get the answer for VCE. Okay, so that's it. This one you can try later. And then that means we have complete our BJT chapter. Okay, so for test 2 will be cover only chapter BJT. Test 2 will be on Friday, another 2 weeks. Okay, for June. So same, you have 2 questions. Okay, first question is test 2 BJT for June 2021. Okay, you will have 2 questions same like test 1. So first part, okay, part 1 and also part 2. So for part 1 you will have a theory question. Theory question will contribute 5 marks, and then calculation 10 marks. Okay, so here you get 15. Same for part 2, also 5 marks and 10 marks. This will contribute to 50% of your carry mark. part 1, okay, for this test, I will only mark first question, okay. Therefore, for another 3 question over here, I will not know what to answer. After the test, when I provide you the marking sheet for your answer, please let me know if you having trouble in getting the marks, because I don't know what you answer. Then I also couldn't help if you have any problem. If you didn't let me know, I won't know anything. Okay, same like this one. If you have anything to ask, or maybe you think that your answer can be considered to get marks, please message me. Okay, don't be shy, just message me. Otherwise, I don't know what happened to all of you. Okay.